start. Welcome to this lecture number 7 of the course Computational Hydraulics. We are in module 2 numerical methods, and in this specific lecture we will be covering unit 3 ordinary differential equation and specifically initial value problem or IVP. So, what is the learning objective for this particular unit? At the end of this unit, students will be able to discretize first order differential equation along with boundary condition, initial condition, because in initial value problem you will have only ordinary differential equation and initial condition. Ordinary differential equation with initial condition can be solved as initial value problem with time or time like discretization. This point is important because always the first order equation may not be time dependent, maybe it is space dependent, and we need to solve that ODE with initial condition to get the solution of initial value problem. ODE can be solved by using finite difference approach, whatever we have covered in lecture 6, and we can use different discretizations to get the solution of ordinary differential equation. Then comes the accuracy. Accuracy of the solution depends only on discretization of ODE. In case of initial value problem, initial condition is like Dirichlet kind of condition, which is specified condition. So, there is no error associated with that initial condition. So, the error comes only from the ordinary differential equation. That is why discretization of ordinary differential equation is important. In general, we can write that ordinary differential equation with dependent variable phi in this format, where d phi by dt is the derivative term and psi t phi is the function which is representing the derivative. Now, with this we need initial condition. This phi at t naught, which is the starting or initial location or initial time level value, phi naught is that corresponding value, psi is a general function. So, this is the basic definition of ordinary differential equation along with our initial condition for initial value problem. In a particular problem, we can have multiple dependent variables. So, we will have multiple ordinary differential equations, and there should be initial condition for each of those differential equations. Now, we need to discretize it numerically. So, from governing equation, if we integrate it from Tn to Tn plus 1, Tn and Tn plus 1 uh, is representing a general time interval. So, we can use mean value theorem to evaluate the right hand side of the above equation. In this case, we can see that this phi n plus 1, which is future time level value, phi n, which is present time level value, plus del t, this is the time increment, and psi is the function. This psi is a function of T n plus theta into delta t. What is this theta? Theta is again a value which is in between 0 to 1. That means we can use any value theta to theta within this 0 to 1. If we use 0, we can get some method. If you use 1, we can get some different method, but with intermediate values we'll get intermediate methods, and in this case phi is also function of T n plus theta into delta t. In this case, we can also include this lower and upper limit for our problems. So, different values of theta, we need to evaluate this psi function. Now, let us see the truncation error. So, phi at T n plus 1 can be expanded as phi T n plus 1 phi t. This is first order derivative. If we expand it further, this is pth order term, and this is p plus 1 order term. In this case, again theta is in between 0 to 1. We can include that 0 and 1 value for our problems. The equation can be written as phi T n plus 1 phi t. This is essentially phi n plus 1 and phi n plus del t into psi T n plus phi, this is comma phi T n and delta t. So, this function is there, plus there will be some truncation error associated with it. So, truncation error, we can use this concept for our initial value problems. If you have theta equals to 0, then we call it as Euler's method, this phi n plus 1 phi n delta t, and this is evaluated at T n phi n. That means, at the starting point we are evaluating the function. Now, if we use p equals to 1 and theta equals to 0 in our Taylor series expansion, obviously you will get this thing only first order term, because this phi T n is essentially psi T n phi n. So, this leading error term is having delta t square value. So, we can say that the order of accuracy for this step is delta t square. But the problem is, when we are considering the Euler's method, we are getting delta t as order of accuracy. Why? Because if we consider this thing, we are to get the derivative, we need to divide it by delta t. So, truncation error in this case divided by delta t, this will give you the actual order of accuracy of the method. So, in this case we are getting first order accuracy. Next, if we geometrically see this thing, then we have one continuous function, and t naught, t 1, t 2, t n, t n plus 1, these are nodal points in the t axis. So, with this, if we calculate the slope at t naught point, that is basically calculating the derivative. This is essentially psi t naught calculation. Now, with this psi t naught value, we can take first step to get this black dot points. White dot points are giving actual values, and black dot points in this case is giving the value that we are getting from Euler's method. So, in this case, if we draw another slope at this black dot point, so obviously virtually we are shifting the curve here, and we are taking the derivative at t 1 point, which is the slope at this particular point. It is important to note that obviously we are getting some amount of deviation from the actual curve. So, error is there. Next is backward Euler method. In backward Euler method, we are calculating the derivative function at future time level. In our Euler's method, we have used T n and phi n. In this case, we are utilizing future time level value. With this, for phi, if we write the expansion, then T n is T n plus 1 minus del t into phi prime at T n plus 1, and this is our leading error. So, this is basically calculating the psi at T n plus 1 and phi n plus 1. So, we can say that we have again this is second order accuracy, but actually we are getting first order accurate Euler method, backward Euler method. So, with this, if we use any intermediate value, so what will be the situation? We need to examine that. So, in this case we are using theta equals to 1 by 2, theta equals to 1 by 2. You can see that in this case we are getting this n plus del t by 2 and phi also evaluated at T n plus del t by 2. Important thing to note that T n plus half by delta t, this is not a nodal point, this is somewhat intermediate point between T n plus 1, this is intermediate point between T n and T n plus 1. So, we need to figure out how to get the approximation for this term. So, first approach we can utilize with Euler's method. With Euler method we can take this phi step. So, with Euler's approximation we are basically multiplying the time interval into, this is evaluated at present time step, that is T n phi n. So, with this information if we write this, this is basically T n plus delta t by 2 plus phi T n plus delta t by 2 into psi, whatever we are getting from Euler's method. So, with this information we can get the phi future level value, that is phi n plus 1. In simplified form we can write this term as K2, where K2 is dependent on K1. K1 is the increment that we are getting from Euler time step. So, in this method we are getting third order accuracy. However, the resulting accuracy for this method will be second order. In second approach we can take average of present time level and future time level, but these are node point values. This is T n, this is T n plus 1. With this, we can use Euler's approximation. So, Euler's approximation for this term, second term, and in this case we can write this with Euler approximation. With this, we can write the final equation in terms of the derivative values psi. This is evaluated at Euler step. Finally, if we write it in a compact form, we can write it as K1, and this is half K1 plus K2 plus order of accuracy is delta T cube. K2 is calculated as delta T into psi T n plus 1 phi n plus K1, and K1 is delta T psi n. This is again third order accurate, and resulting thing will be second order accurate. Then comes this Runge-Kutta method. In Runge-Kutta method, we can use this different values of increments, and these increments are explicit in nature. Explicit means that on the right hand side in the function psi, only known values are there. In this case, K2 in the left hand side, K1 in the right hand side. So, whatever value is calculated from K1, that will be transferred to this psi calculation for K2. Again, this calculated K2 will be transferred here, K1 and K2. Similarly, for Km, we can get K1, K2 to Km minus 1. So, this method is explicit in nature. We can directly get the value of Km without any matrix solution or any other method. Further, this Runge-Kutta method is defined in terms of this weighted assembly of increments. This is phi n plus 1 equals to phi n, this W1 K1, W2 K2, Wm Km, and this parameters Cj, Aij, Wij can be obtained by matching the corresponding expansions with Taylor series. So, we can expand these increments around these points Tn and phi n, and we can get different values of Cj, Aj, Wj. If we consider second order Runge-Kutta, then we have only two terms or two increments, K1 and K2. We need to find out what is K1, C2 and A21, and W1, W2. We can get it from Taylor series expansion, and if we finally write the solution, this is K1 and K2 is evaluated at 2/3 delta t and t at Tn plus 2/3 delta t and phi n 2/3 k1, and overall accuracy is del t cube, but finally this is second order accurate method. In third order RK, we need to consider 3 terms, 1, 2 and 3. Similarly, we can get the values for C2, C3, C2, C3, A21, A31, A32, W1, W2, W3 from Taylor series expansion. And if we write the final expression, we can write it as RK3, and interestingly in this case it is evaluated at half time step for the intermediate K2, and for others it is at initial, and this is at final time step, and these are coefficients -1, 2, and finally we can write it as fourth order accurate, but final accuracy will be of third order. Similarly, for fourth order RK, we can use this approach and we can get fifth order accurate scheme, but final accuracy will be of order 4. And interestingly in this case, this K2 and K3 are calculated at half time step or at the middle of the 2 nodal points. So, if we consider one practical example of this, this is del 2 y by del y by del x S naught minus SF 1 minus FR square. This is well known equation for describing the gradually varied flow in open channels. This is ordinary differential equation, first order, and with initial condition, that means depth is specified at some spatial location. You can see that on the right hand side we have this S naught minus SF 1 minus FR square term. This is function psi, which is function of x y, S naught minus SF 1 minus FR square. S naught is bed slope, SF is energy slope, 1 minus Froude number square. So, essentially in this case we get psi as function of y only, which is depth in the channel, flow depth in the channel. So, this is a typical example of initial value problem. In the next lecture, we will be discussing boundary value problem for ordinary differential equation. Thank you.